Find the point on the curve y equals the square root of 2x plus 2 that is closest to the point 2, 0. Now, before we actually tackle this problem using calculus, I think it's useful to visualize what the question is actually asking. The function y equals the square root of 2x plus 2 is a transformation of the common function y equals the square root of x. And to see exactly what combinations of transformations are involved, we can rewrite the square root of 2x plus 2 as the square root of 2 times x plus 1, and then use the fact that square roots can be applied separately to factors of an expression to rewrite this as the square root of 2 times the square root of x plus 1. Writing it this way is useful because it lets us see that the two transformations that are happening is we have a vertical stretch by a factor of the square root of 2 because we are multiplying by square root of 2 outside the square root, and we have a horizontal shift of left 1 unit because we have x plus 1 inside the square root. So remember if you see something added to x inside the function, that's actually a shift left, and if there's something being subtracted from x inside the function, then that is a shift to the right. This allows me to make a rough sketch of the graph of this function. I'm not trying to make it perfect. I just want to get an idea of what it looks like. An untransformed square root function graph would go through the points 0, 0, and 1, 1. So the vertical stretch by a factor of square root of 2 would take the point 0, 0 and leave it alone because multiplying the y by root 2 does nothing if the y value is 0. And it would take the point 1, 1 to 1 square root of 2. Again, we're just multiplying the y values by the square root of 2, which gives us a slightly steeper looking curve with the same general shape as the square root function. And finally, if we shift the whole graph 1 unit to the left, that will take the point at 0, 0 to the point negative 1, 0, and it will take the point 1 square root of 2 to 0 square root of 2. So that is what y equals the square root of 2x plus 2 looks like. Now, the purpose of drawing this graph is to understand what is being asked when we're asked to find the point on the curve that is closest to the point 2, 0. Do you technically need to do all of this to do the calculus? No, but if you're having trouble understanding what the question is asking, this can be super useful. So I'm going to redraw my graph one more time so that I don't have my intermediate functions in there. I'm just going to show the function I care about, y equals the square root of 2x plus 2. And the point we're interested in is the point 2, 0. And so the question is asking what point on the curve is the closest to the point 2, 0. To determine that, we need a formula that tells us how far any point on the curve is from the point 2, 0. So if I pick just a random point, x comma y, on the graph of y equals the square root of 2x plus 2, what I want to do is come up with a formula first for the distance from the point xy to the point 2, 0. Our goal is to minimize the distance. And anytime we want to minimize or maximize something, we first have to have a formula to calculate it. So our first step is going to be to write a formula for the distance between the point 2, 0 and any point on the curve y equals the square root of 2x plus 2. Lucky for us, there's a formula for the distance between 2 points. It's called the distance formula. It's essentially just the Pythagorean theorem, but it says that the distance between 2 points is the square root of the sum of the squares of the distances between the points. The distance formula says that the distance between 2 points x1, y1, and x2, y2 is equal to the square root of the sum of the squares of the difference between the x values and the difference between the y values. If you're wondering what that has to do with the Pythagorean theorem or where it came from, if we look at our picture and we make a right triangle where the hypotenuse is the segment that can If we make a right triangle where the hypotenuse is the segment that connects, if we make a right triangle where the hypotenuse is the segment that connects our 2 points together, the length of the hypotenuse is the distance we care about. The length of the base is the difference in the x values. So that would be x2 minus x1. And the height of the triangle is the difference in the y values, which would be y2 minus y1. Now this problem is very specific because we're talking out of now this problem is very specific because we care about a very specific point, 2, 0. So the first thing we can do is rewrite our distance formula, replacing x1 with 2 and y1 with 0, so that we're looking at the distance from a point xy to the point 2, 0, like the problem asks us to. Now we can go even further than that, because if our point x2, y2 is really on the curve y equals 2x plus 2, then if I pick a specific x value, then the y value that goes with it has to be the square root of 2 times the x value plus 2, because that's what it means to be on the curve y equals the square root of 2x plus 2. It means that if your x coordinate is x, then your y coordinate is the square root of 2x plus 2. So we can replace the y2 in our formula with the square root of 2x plus 2. And now we have a function for the distance that only depends on x. We're going to need to take its derivative later. That's how we find maximums and minimums of functions. So it's in our best interest to clean it up just a little bit to make that derivative finding process simpler. So to clean this up, I'm going to start by expanding x minus 2 squared. You can do this as side work if you want. X minus 2 times x minus 2 is x squared minus 2x plus 4. So x squared minus 4x plus 4. And then for the second half of the expression underneath the square root, I have really just the square root of 2x plus 2 squared, because subtracting 0 doesn't do anything. But when you square a square root, the square root just goes away. So we're left with x squared minus 4x plus 4 plus 2x plus 2. And then a very small amount of combining like terms gets us to x squared minus 2x plus 6 inside the square root. And this is the function that we want to optimize. So in terms of our goal, we've completed the first step. We're trying to minimize the distance. We now have a formula for that distance. So our next step is going to be to find the derivative and then use that to find the critical numbers. Remembering that the critical numbers are candidates for where our function could have a minimum or a maximum. So to find the derivative, I'm going to rewrite this function in a slightly different way. This is not at all required, but I think it helps some people. So if I write the square root as a power of 1/2, I get that the distance is x squared minus 2x plus 6 to the 1/2. So that when I take the derivative, I can start by using the power rule. The 1/2 comes down, and the new exponent is 1/2 minus 1. But then the inside was itself a non-constant. Then the inside was itself a non-trivial function of x. But then the inside itself was a function of x. So now I need to do the chain rule. So I have to multiply by the derivative of the inside. So I'm multiplying by the derivative of x squared minus 2x plus 6. And the derivative of x squared minus 2x plus 6 is 2x minus 2. So I have that the derivative is 1/2 x squared minus 2x plus 6 to the negative 1/2 times 2x minus 2. And I can rewrite this just a little bit more. So I have a factor of 1/2, and then I have 2's in both terms of the 2x minus 2. So I could factor the 2 out and then cancel it. So to make that a little bit more clear what I'm doing, if I factor the 2 out of 2x minus 2, then I can cancel the 1/2 from the power rule with the 2 from when I took the derivative of the inside, and it leaves behind an x minus 1. And then to write my function with a square root again, the x squared minus 2x plus 6 was raised to the negative 1/2 power. So I can write that as x squared minus 2x plus 6 inside a square root in the denominator. Square root gives me the 1/2, the in the denominator makes it negative. Now I need to find the critical numbers. So I'm looking for places where my first derivative is either 0 or undefined. A fraction can only be 0 if the numerator is equal to 0. So asking where d prime of x is equal to 0 is the same as asking where is x minus 1, the numerator, equal to 0. So one of my critical numbers is x equals 1. To determine where a fraction is undefined, then we need to look to see where is the denominator equal to 0. So the square root of x squared minus 2x plus 6 will equal 0 when x squared minus 2x plus 6 equals 0. I don't think that I can factor that, so instead I would use the quadratic formula. But when I do, I notice pretty quickly that the expression underneath the square root, so the b squared minus 4ac given by the quadratic formula, this is also known as the discriminant, is equal to 4 minus 24, which is negative. So if I end up with a negative underneath the square root, that means that there are no real solutions to this. Since there's no places where that denominator equals 0, I also don't have to worry about it being negative, which is important here because since there are no places where x squared minus 2x plus 6 equals 0, I can also guarantee there's no places where it is negative because I can tell it's a parabola opening up because the leading coefficient is 1. So if it was ever negative, it would have to equal 0 in at least one place. So the fact that it never equals 0 means the whole parabola is above the x-axis, so it's never negative. The reason I care about that is because it's inside the square root, so I potentially could have places where my derivative's undefined just because I have a negative underneath the square root. Those aren't necessarily going to be places where I might find, those aren't necessarily places I need to check for local mins and maxes, but it's good to be aware. But we don't have to worry about that here. So we only have one critical number. And if we go back and look to our graph, that critical number was at x equals 1. So the point that that critical number corresponds to is 1 comma the square root of 2 times 1 plus 2, which is 1 comma the square root of 2 plus 2, so the square root of 4, which is the point 1 comma 2. And it certainly looks like from my graph that that's a reasonable answer that would minimize the distance. But if I want to be absolutely sure that that critical number is actually giving a minimum, I need to do some sort of additional test. And there are multiple ways to do this. One way would be to look at the first derivative. The fact that I have only one critical number means that I'm dividing the number line into two segments, the interval from negative infinity to 2 and the interval from 2 to infinity. So to test to see if 2 is really a location of a minimum, I just need to see what's happening on either side of 2. So I can test a value like x equals 1 and a value like x equals 3 and see if my first derivative is positive or negative on those intervals, because I know that if my first derivative is positive, that means my function is increasing, and that if my first derivative is negative, the function is decreasing. So here, if I look at d prime of 1, I get 1 minus 1 over. So to test the critical number x equals 1, I have a couple different options for doing that. The first would be to look at the first derivative. Because I have only one critical number, it divides the number line into two pieces: the interval from negative infinity to 1 and the interval from 1 to infinity. So to test to see if x equals 1 truly gives me a minimum in the distance, I can test a point that's less than x equals 1, so I'll use x equals 0, and I can test a point larger than 1, like x equals 2. And I'll remember that if my first derivative is positive, that means my function is increasing. And if my first derivative is negative, that means the function is decreasing. If I look at the first derivative evaluated at 0, I get 0 minus 1 over the square root of 0 squared minus 2 times 0 plus 6. Now it does not actually matter what the value of this expression is, only if it's positive or negative. So if I simplify it just to negative 1 over the square root of 6, I can tell that's a negative number. That tells me that my function is decreasing on the interval negative infinity to 1. That's a good sign, because if it's going down as we approach x equals 1, then it quite possibly has a minimum at x equals 1. But it's not enough to check just one side, because some functions will decrease and then flatten out at the critical number and then continue to decrease and then continue to decrease afterwards. So you really do have to check both sides. If I look at the first derivative evaluated at 2, I get 2 minus 1 over the square root of 2 squared minus 2 times 2 plus 6. And again, I'm not super interested in the actual value of that, just whether it's positive or negative. And I get 1 over the square root of 6, which is a positive number. So my function is increasing on the interval 1 to infinity. That means that we do in fact have a local minimum, because our function went down and then up again. And because this was our only critical number, the only other thing that we could reasonably check would be, are there any endpoints to this function? So a lot of times when we find mins and maxes on an interval, we have a starting x and an ending x. If we go back to our graph, we can see that there's no ending x, because this graph goes on forever. X goes to infinity and we still have this square root curve. Clearly those points are going to be farther away. But we do have a starting x, because the square root function starts at x equals negative 1. But we can see that that point, just based on our picture, is 3 units away from the point 2, 0, which is farther away than the point we found 1, 2. And you could verify that by actually plugging x equals 1 into the distance formula that we got. All of this goes to show that the closest point is the point 1, 2. Now I mentioned that there were other ways to test to see if that is the closest point. The other method that you could use instead of doing the first derivative test and looking at the number line is you could have used the second derivative test. But that would involve taking our d prime of x function and differentiating it again. I would argue that finding the second derivative here is much more complicated than just plugging in a couple values on the number line. So while I could do that method, it's certainly not the most efficient method for this problem. But if you wanted to do it, you would find the second derivative, plug in x equals 1, our critical number, and see if the result you got was positive or negative. If you got a positive number, that would mean the graph is concave up. That would mean you found a local minimum. If you got a negative number, that would mean the graph is concave down and that you had found a local maximum. If you got 0, which does sometimes happen, then the test fails and you would have to go back and use the first derivative test anyway. But that is an option, but I definitely only recommend it for times when the second derivative is either easy to compute or you needed it for something else anyway.